All right, guys, this is for your states of matter. We're going to talk about density, buoyancy, and viscosity. All right, what is matter? What's the matter with you? Anything that has mass and takes up space. So pretty much anything you can imagine, from the air we breathe to water we drink to the sun and all the stars. So did you ever think that air, what we breathe in, well, we breathe in a lot of stuff whenever we take a breath, but the stuff that we need to live is molecular oxygen, O2. That's two oxygen molecules that are bound together. Regular elemental oxygen is actually not too good for you. And O3, if you added one more, is called ozone, and that's pretty bad. So we don't breathe in any one of those, but either way, if you look at the periodic table, each molecule of O has about 16. If you look at the number on top of the periodic table, it's like a 15.9 and a bunch of other stuff. So we just go ahead and say it's about 16. That's 16 mass units, and that ends up being important later on. But essentially, you need to understand that air is not weightless. It has a mass, and it arranges itself based on density like all other things. So if you were to look at like a jar of tea or something like that, right? This is a really bad jar of tea, but whatever. Over time, what do you notice? If you let it settle for a while and you didn't mix it particularly well, you would end up with some stuff that kind of settles at the bottom. And then you would have some solvent that takes up the rest of this, right? So even something that seems like it's mixed and distributed evenly over time will end up kind of settling out and arrange itself by density. Oxygen is the exact same thing with the other molecules in the atmosphere. What are physical properties? Let's see. Density. Ways to measure matter. We have mass, we have volume. So this is something we talked about earlier when we were defining whether something's a solid, liquid, or gas. We look at things like the volume. Okay, density. Density is a property that relates mass and volume. It combines them. Density is mass divided by volume, so you need to make sure you know that. This is a triangle that you need to know. Okay, so you can know that density equals m over v, or you can know this triangle right here. Okay, this is big V this time, big V, not little v like velocity, and this is capital D for density, not little d like distance. So remember that when we are going over, we're going to divide, and when we go across, we're going to multiply like that, okay? And density equals mass per unit. So usually the unit we're going to use, the System International unit, is grams per cubic centimeter. That's how you say that. So this is grams per centimeter cubed. All right, density affects hardness, so resistance to scratching, elasticity, the ability to stretch and return, brittleness, the likelihood to shatter, malleability, so if something is malleable, you're able to hammer it down into sheets, and tensile strength, so how much force before breaking. So you think about the tensile strength of like a piece of paper. If you pull it apart, it rips pretty easily, versus like rope or even human hair. Human hair has pretty good high tensile strength. Spider web has really high tensile strength. Steel cable, really, really high tensile strength. Density of fluids. Density tend to be a little bit less dense than solids. Molecules move around easily. They do not stack easily, they slide around. Water is the exception. Ice is less dense than water due to the structure of water when it's frozen. That's because water likes to do this thing where it makes like a hexagonal. So at each one of these points right here, these would be oxygens. And the way that they like to repel each other with their little electrons, they end up forming these crystalline structures like this. And in the middle, there's a lot of space that you can put air. So that's why igloos in the North Pole, or in the high latitudes and really low latitudes, igloos are ways that people kind of have traditionally used to stay warm because they pack a lot of air in there, and you know that air is an insulator, right? So that's just a little extra information in case you didn't know. All right. Okay, the density of material can be determined by dividing the mass and the volume. Okay, so this is something we just did right now. So for example, what is the density of a 400 gram block? So gram is that mass, density, or volume. So grams is how we measure a mass, so make sure you show that work. And it has a volume of 16 cubic centimeters, so it already told you its volume, so that's V. So we're looking for the density. This is how you get your points right here, right, when you're showing work for me. So we have our givens right here. We have our unknown here, so that's 2 points. And then let's look at our equation. Our equation is going to be d mass over volume. So that's going to be density, I just messed up, capital D. Density equals mass over volume. Okay, what gets plugged into mass? Is it 400 or 16? Well, we labeled this M, so this 400 has to go here, on top, right? And we labeled volume on the bottom, and this is V, so this is going to go down here. So we should have 400 over 16. So this, you get another point for showing the equation correctly, and another point for plugging in correctly. And your final answer is going to be 25 grams per cubic centimeter. Okay, moving on. Sometimes the mass is given in a unit other than grams, okay? Or the volume is given in a unit other than milliliters. So let's look at an example of that. Okay, what is the density of a block that weighs 2.5 kilograms? So kilograms, is that mass, volume, or density? That's going to be mass. And has a volume of 40 cubic centimeters. Okay, 40 cubic centimeters. So that's going to be, again, volume, V. Okay, so what is the density of that? So our unknown this time is going to be D for density. Okay, still. Okay, so down here we have our triangle, D. Got distance stuck in my head here. Distance, mass, and volume. Okay, so we're looking for this guy, so we're still going to be dividing like that, okay? So our density equals mass over volume. We have to make sure if we're going to do grams per cubic centimeter, we have to convert these kilograms into grams. So if you remember from the beginning of the year, we had our king, hector, demanded, here's our center unit, mlg. More delicious chocolate milk. We have to go ahead and convert that back into grams. So we're starting here, and we need to end here. So we're going to jump to the right 1, 2, 3 times. Okay. All right. So we had 2.5 kilograms. 1, 2, 3 to the right. Add these zeros, and that's the number of grams that we had. Okay, and that's where they got that 2,500 from. So on top, we're going to have 2,500 over 40 cubic centimeters, and that comes out to, what is this ugly stuff? Let's get it out of the way. Sorry, ugly stuff. 62.5 grams per cubic centimeter. Okay, moving on. A cubic centimeter is equivalent to an ml, a milliliter. You need to know that. That's something you need to know. A milliliter will take up a cubic centimeter. Specifically, milliliter is used for volume of gases and liquids, and a cubic centimeter is used for the volume of solids. So cubic centimeter for solids, milliliter is for gases and liquids. Okay, so I color-coded that for you. You might want to circle that and maybe connect them somehow, right? Connect those. Okay, let's talk about buoyancy. Buoyancy is the measure of the upward pressure a fluid exerts on an object. Okay, and some of y'all who did vocabulary, you might have drawn that. It's determined by the density, which we just did earlier, right? So again, who can remember what the equation for density is? Density is m over v. Okay, so this right here is very important. The denser the fluid, the more buoyant force it applies. It's ruled by Archimedes' principle. The force exerted on an object by liquids is equal to the mass of a fluid displaced by that object. Displacement. What does displacement mean from what we said earlier? Displacement, remember, at the beginning of the year was the distance between point A and point B. So this distance right here, the straight line distance. So even if I went all over the page like that, the displacement would still just be the green. The distance would be red, but the displacement is green. Okay, so what does it mean to be displaced? To move something from its usual place. So usually you see that in like a beaker. You might have done this lab in like middle school or something, where you had water level here at the beginning. This is part A, and at the end you put like a rock in or something like that in the bottom, and the volume of that rock ends up pushing the water upward to up here. This would be part B, right? So the displacement would be from here to here. Okay, if buoyant force is greater than the mass of the object floats. If the buoyant force is less than the mass of the object sinks. Okay, so we're really basically here is we're comparing densities. So if we compare the density of the solvent, or the object that's being placed in versus the object it's being placed in, so if that rock, for instance, in the previous page, so if that rock, this guy right here had a density of, let's say, like 2, and the density of the solvent, the water that it's in, had a density of 1. Well, since 2 is greater than 1, that's why 2 finds itself trying to finding itself at the bottom of this mixture here. Okay, neutral buoyancy is achieved when the mass of the object is equal to the mass of the liquid. The object floats exactly in position that's being placed. So if you've ever jumped in the water, right, and like you as a person, you jumped in the water, and for this you're green, you notice when you just hold your body out, which is kind of you're standing straight up or whatever, you kind of are just right here, right? You're not quite on top of the water, but at the same time you're not all the way at the bottom. That's because you have somewhat of a neutral buoyancy. You're 70-something% water, so you're going to be pretty close to neutral buoyancy with the water there. Okay, if you were to curl yourself up into a ball, and you made yourself like this, though, you took all your mass and you became that, well, what would happen is you have the same mass, but your volume has decreased, right? So because your volume's decreased, what happens to your density? It goes way up, and so you're going to sink, and you're going to be down here. If you were to spread yourself out really, really wide, you notice that you have the same mass, but now your volume has increased. So as a result, your density is going to go down, and you're going to float. So these are different ways that you can keep yourself afloat in the water. That's why they tell you to become a plank. Or if you want to dive, you want to become very pointy, like a diver, go to the bottom. Okay, viscosity. The measure of a material's resistance to flow, how hard it is to pour. So you can think of things like syrup versus water, right? Okay, viscosity is determined by the size of the liquid molecules, the shape of the molecules, and the temperature of the liquid. This also applies to gases. So think about it. If you were to heat up, syrup, it'd be a little bit easier to pour, or like butter or something like that, right? A thick substance is described as being very viscous. Ketchup and syrup cold are going to be viscous. Motor oils have different grades based on viscosity. So 10W40, 10W30, those are going to have different viscosities. Viscosity of a liquid. As the temperature of a liquid increases, its viscosity decreases. That means it becomes a little less dense, right? The additional kinetic energy, so you're raising the temperature. What is temperature? Remember, temperature is the average kinetic energy of a substance. So think about it like this. If I have a bunch of little molecules that are like this, and then I add some energy to it, so plus energy, what's going to happen is they're going to be able to move further apart because they now have higher speed, right? So their velocity goes up. Okay, so if they're a little bit less dense, guess what? They're not going to stick together as much, and they're going to pour a little bit easier. Okay, so additional kinetic energy allows the molecules to slide past each other with greater ease. Temperature in gases. As the temperature of a gas increases, its viscosity increases. Okay? Because gas molecules are far apart, they do not have to slide over each other very often in order to flow. Raising the temperature actually increases the number of collisions between molecules, resulting in an increase in friction and therefore viscosity. So interesting, right? Okay, check it out, watch what happens. We can't really do that. Okay, 4 states of matter. We've got solid, liquid, gas, and plasma. So you're familiar with 3 of these. The 4th one you may not be. Okay, solid state, lowest energy form of matter. Molecules do not change position. They have definite shape and definite volume. Definite shape, definite volume. Lowest energy. Molecules do not change position, at least not easily. Okay, liquid state. Molecules can move. They have definite volume, but indefinite shape. It takes the shape of the container. Okay, gas state. Molecules also move freely, so liquids and gases can move freely and separate from one another. That's something that's a little different. The gases are able to separate particles from each other very easily, whereas liquids are they have cohesive forces in liquids. So with cohesion. I spelled that wrong. Oh well. Okay, no definite shape, no definite volume. Okay, plasma. Plasma is the most common state of matter in the universe. It's basically charged gas. It's the highest energy form of matter. It's made up of ionized, so ionized means it has a charge. The 2 charges we can have are plus and minus. These are going to be cations right here. And these right here, anions. Don't worry about that quite yet, but if you're looking for something else to know, that's something you know. Ionized gas. So that would be like if I had a hydrogen molecule, or a hydrogen atom rather, and I were to add energy to it, I would end up with an hydrogen without an electron. So this guy right here usually has a little electron that floats around in a circle, and it likes to float around in orbit like this, and it has one proton in the middle. We'll go ahead and draw a proton real quick. So one proton, okay? But if I add energy to it, I'm allowing this electron to escape. So it's just going to be the proton in the center once I energize it, and then there will be a free-floating electron somewhere in the universe. So free-floating little electron. So here's the minus charge, and this guy over here is going to be left overall as a +1, because protons are +1, electrons are -1. So if I get rid of the little negative guy, I'm left as a positive. So this right here is what we call ionized matter, and it's going to be, that's what plasma is. Okay, atoms breaking apart due to high heat energy. All right, so that's all you need to know for right now. I hope this was helpful.